Learning Goals. Welcome to this learning session on acid rain, causes, effects, and reduction. In this course, we shall address introduction and primary pollutants, chemical reactions of acid rain, environmental and structural impacts, emission reduction and mitigation, global efforts and future outlook. There will be a quiz at the end to test your knowledge.
Introduction to acid rain. Rainwater is naturally slightly acidic due to the dissolution of carbon dioxide from the atmosphere, forming carbonic acid. However, acid rain refers to precipitation that is significantly more acidic than normal, typically with a pH level below 5.6. This increased acidity is primarily caused by atmospheric pollutants. The pH scale measures acidity, with lower values indicating higher acidity. Normal rain has a pH of around 5.6, while acid rain can have a pH as low as 4.0 or even lower in severely affected areas, making it comparable to vinegar or lemon juice in acidity. Sulfur dioxide, primary pollutant hydrocarbon fuels, such as coal and oil, often contain impurities in the form of sulfur compounds. When these fuels are combusted in industrial processes or power generation, the sulfur within these impurities undergoes oxidation. This chemical reaction leads to the formation of sulfur dioxide. Sulfur dioxide, SO2, is a colorless gas with a pungent, irritating odor. It is a major air pollutant primarily released from industrial activities, especially from power plants burning fossil fuels. Globally, coal combustion accounts for approximately 50% of anthropogenic sulfur dioxide emissions. Once released into the atmosphere, sulfur dioxide can dissolve in rainwater. This dissolution forms sulfurous acid, contributing directly to the increased acidity of precipitation. This acidic solution is a key component of acid rain. Nitrogen oxides, another source. Unlike sulfur dioxide, oxides of nitrogen, NOx, are not produced from impurities within hydrocarbon fuels. Instead, they form when nitrogen and oxygen, naturally present in the air, react together at extremely high temperatures. These conditions are typically found inside vehicle and aircraft engines. The intense heat generated during the combustion process in engines provides the necessary energy for atmospheric nitrogen and oxygen to combine. This reaction forms various nitrogen oxides, such as nitrogen monoxide, NO, and nitrogen dioxide, NO2, which are then released into the atmosphere through exhaust fumes. Nitrogen dioxide is a toxic, orange-brown gas with a sharp smell, distinct from carbon monoxide. The formation of nitrogen dioxide, a significant component of NOx, involves atmospheric nitrogen reacting with oxygen at high temperatures. This specific reaction is crucial in understanding how vehicle emissions contribute to acid rain. Similar to sulfur dioxide, nitrogen dioxide is a non-metal oxide that readily dissolves in rainwater. When it dissolves, it forms nitric acid, which is a strong acid. This process further increases the acidity of precipitation, intensifying the effects of acid rain on the environment. Impact on aquatic ecosystems. Acid rain significantly harms aquatic ecosystems by increasing the acidity of rivers, lakes, and streams. This change in pH can be lethal to many aquatic organisms, including fish, amphibians, and insects, which are sensitive to even small alterations in water chemistry. For example, most fish species cannot survive in water with a pH below 5. Beyond direct toxicity, increased acidity can also leach aluminum from soils into water bodies. This dissolved aluminum is highly toxic to fish, impairing their gill function and making it difficult for them to absorb oxygen and salts. This leads to widespread mortality and a reduction in biodiversity in affected aquatic environments. Damage to forests and vegetation. Acid rain causes significant damage to forests and other vegetation, particularly in mountainous regions where clouds and fog are more acidic. It directly harms leaves and needles, weakening trees and making them more susceptible to disease, insect infestations, and extreme weather conditions. This can lead to widespread forest decline and reduced growth rates. Indirectly, acid rain also acidifies the soil, leaching essential nutrients like calcium and magnesium that trees need for healthy growth. Simultaneously, it mobilizes toxic metals such as aluminum, which can then be absorbed by tree roots, further damaging them. This dual effect of nutrient depletion and increased toxicity severely impacts forest health and productivity. The damage is often visible as pitting, black crusts, and loss of carved details on historical monuments and architectural facades. For instance, many ancient Greek and Roman sculptures and buildings have suffered irreversible damage from acid rain over the past few decades, far more than in previous centuries. This not only causes aesthetic damage, but also compromises structural integrity. Reducing sulfur emissions. One effective strategy to reduce acid rain is to prevent sulfur dioxide formation by removing sulfur from hydrocarbon fuels before combustion. This process, known as desulfurization, is typically carried out at oil refineries. By treating petrol, diesel oil, and fuel oil, the sulfur content can be significantly lowered. A common method for desulfurization is hydrodesulfurization, HDS, where fuels are treated with hydrogen gas over a catalyst to convert sulfur compounds into hydrogen sulfide, H2S. The H2S is then captured and converted into elemental sulfur, which can be safely stored or used in other industries, thus preventing its release into the atmosphere as SO2. Flue gas desulfurization. Another critical method for reducing sulfur dioxide emissions is flue gas desulfurization, FGD, often referred to as scrubbing. This technology is installed in the chimneys of power stations and large industrial plants to remove SO2 from the exhaust gases before they are released into the atmosphere. It is a post-combustion control measure. The most common type of FGD system is wet scrubbing, which involves spraying a slurry of limestone, calcium carbonate, or lime, calcium hydroxide, into the flue gas. The SO2 reacts with the alkaline slurry to form calcium sulfite or calcium sulfate gypsum, which can then be collected and disposed of or even reused. This process can remove over 90% of SO2 from emissions. Neutralizing acidic environments. To counteract the effects of acid rain on already damaged ecosystems, measures can be taken to neutralize the excess acid in affected areas. This often involves adding alkaline substances, such as calcium carbonate, limestone, or calcium hydroxide, lime, to acidified fields and lakes. This process is commonly known as liming. Liming helps to raise the pH of the soil and water, making the environment more hospitable for plants and aquatic life. While effective in the short term, liming is a temporary solution that requires repeated applications and does not address the root cause of acid rain. It is often used as a restorative measure in severely impacted areas, such as acidified lakes in Scandinavia. Global efforts and future outlook. Acid rain is a transboundary pollution problem, meaning pollutants released in one country can travel long distances and cause acid rain in another. This necessitates international cooperation and agreements to effectively address the issue. The Convention on Long-Range Transboundary Air Pollution, CLR-TAP, is a key international treaty aimed at reducing air pollution across Europe and North America. Significant progress has been made in reducing acid rain in many regions, particularly in North America and Europe, through stricter emission controls and technological advancements. However, challenges remain, especially in rapidly industrializing parts of Asia, where emissions of sulfur dioxide and nitrogen oxides continue to be a concern. Continued global efforts are essential to mitigate the long-term impacts of acid rain and protect ecosystems worldwide.
Summary. Well done. You have completed the course Acid Rain, Causes, Effects and Reduction. You should now be familiar with Introduction and Primary Pollutants, Chemical Reactions of Acid Rain, Environmental and Structural Impacts, Emission Reduction and Mitigation, Global Efforts and Future Outlook. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.